In this video, we talk about electrochemistry. Electrochemistry deals with reactions, chemical reactions that involve movement of electrons. So, if we consider this reaction here, this reaction can be regarded as an electrochemical cell. So, electrochemical cell. It's like a battery. It is a cell that uses movement of charges. In this case, positive and negative charges. So if you look at the equation, you see that the zinc here is losing electrons. So zinc is losing electrons to form zinc ion, while copper is gaining electrons to form copper solid. So we are saying that copper ion is gaining electrons to form copper solid. So a reaction like that is a redox reaction. So reduction and oxidation. We know that oxidation is loss of electrons. So oxidation here is loss of electrons. So we see zinc loses electrons. Reduction is gain of electrons. So copper ion gains electrons. So if we look at this reaction, we can group it into oxidation and reduction by writing half equations. A half equation of oxidation and a half equation of reduction. So if you are talking about oxidation, this is the half equation for oxidation. So zinc to give us zinc ion and 2 electrons. So for oxidation, the electrons are the products. In terms of reduction, we have reduction here, copper ion plus 2 electrons to give us copper solid. So let's look at the terms anode and cathode. So an anode is where oxidation occurs. So where oxidation occurs. While a cathode is where reduction occurs. So what do we mean by that? So let's look at the diagrams to the right there. They will give us information about oxidation and reduction. So if we look at these diagrams, we see in the first diagram above, this diagram, we see that we have a zinc strip in copper sulfate solution. So in this case, the zinc strip is the zinc solid. The copper sulfate solution is the copper ion. So we have zinc solid in a solution of copper ion. And since zinc is undergoing reduction, it is going like to be eaten away with time. So the zinc strip is going to dissolve in copper sulfate. Why is zinc strip dissolving in copper sulfate? Because it is changing from copper solid to, or it is changing from zinc solid to zinc ion. So in this case, it is dissolving. As it is dissolving in the copper sulfate, the zinc is losing electrons. Now, where do the electrons go? Electrons move from zinc. So this is electron. The electrons move from zinc to copper. So as copper is dissolved, as zinc is dissolving, it is making copper solid. So copper solid is being formed and zinc is dissolving. So based on this, we go to the diagram on the right here. We see that the zinc strip will be coated by copper. So it will have a copper coating, indicating that this redox reaction is forming copper solid. So the coating is the copper solid, while the dissolution is forming zinc ion. We can show that using what we call a cell diagram. So here, if you look at a cell diagram, now we are not just putting a zinc strip in copper sulfate. Here what we are doing is we have a zinc strip but in zinc sulfate. So each strip is put in its own solution. Here we have a copper strip in copper nitrate. So we have separated the two solutions by a salt bridge. So the salt bridge contains potassium nitrate. So here you have a potassium K plus and NO3 minus. When you combine the two, you have potassium nitrate. Now, if we look at the salt bridge and see the movement of ions on the salt bridge, we will see that the cation here on the salt bridge, which is this cation, the cation on the salt bridge is moving towards cathode. So what it means is this strip is called a cathode because that's where cations go. So by definition, cathode is where cations go. So the term cathode is coming from cation. Now if you look at the nitrate here, the nitrate is approaching where the anode is. So because the nitrate is an anion, so an anion goes to anode. So anode is where anion go. So that's where the names cathode and anode come from. Now if we get rid of this and continue, if you look at the cell diagram here, you have a glass wool here to form like a barrier. You have these two strips, a strip of anode, a strip of cathode. So these strips are known as electrodes. Electrodes are where redox reactions occur in a cell. So if you want redox reactions to occur in a cell, then you need to have electrodes. You can have two types of electrodes, or you can have a single type of electrode. So when we talk about electrodes in this case, we have anode and cathode. These are two examples of electrodes. So in terms of a cell diagram, usually the anode will be a metal strip, and the solution will be the solution from that metal. So here this is zinc. The solution here is zinc nitrate. This one is copper. The solution is copper nitrate. Now you need to connect the two using the salt bridge. So we'll try to define what the salt bridge is. Really, the salt bridge just allows the movement of these ions, the ions we call the counter ions, potassium and nitrate. So the counter ions complete the circuit. Without these counter ions, you will not have a light here, because the circuit, the electrochemical cell, the electric circuit, needs to be completed using the salt bridge. So this is a normal diagram of a cell. So if I'm looking for a diagram, I would expect you to be able to tell me what is the cathode, what is the anode, and where is the salt bridge, and then where do the electrons go. As you can see here, electrons move from anode all the way to cathode. So electrons move from anode to cathode. So take note of that. So those are the things that you need to understand. And we see that at anode here we have oxidation. So we have loss of electrons. At cathode, we have gain of electrons. So what do we mean? You can see after oxidation, the electron is lost from this zinc, and it goes all the way to the copper. So the copper, when the electrons get here, the copper ion in solution will attach to the electrode to receive the electrons and then form a solid. Now, you can draw this same diagram in a condensed way. So how do you do that? You can draw this diagram using a line notation. So line notation is the one that we see here. In line notation, you say, what do I have? In oxidation, I have zinc. You start with the oxidation. I have zinc, which is a solid, but this zinc is forming zinc ion. So you have a line here and say zinc is forming zinc ion. So this zinc ion is in aqueous form. This is the first reaction. You ignore the electrons. Then you write two lines. These two lines stand for salt bridge. So the two lines stand for salt bridge. Then from there, you go to reduction. So this part is oxidation. After the salt bridge, you have copper, which is aqueous, and then it will give you copper solid. So this part is reduction. Oxidation is on the right, reduction is on the left. This diagram is known as a line notation. So you need to be able to learn how to write line notation diagrams. Oxidation on one side, reduction on one side. As you can see here, we have solid at one end and solid at the other end. Now, you may have certain situations where you are starting with a solid, but you are not forming another solid. For example, here, our products are in aqueous phase. They are not solid phase. Here, iron is a solid, but we don't have a solid in here. So if you get that situation, you use an electrode that is inert. So in this case, our inert electrode is platinum. PT, inert electrode. So really, the inert electrode does not get reduced or does not get oxidized. It just provides surface for oxidation or reduction. So the inert electrode provides surface for oxidation or reduction without itself involved. So you say, because we are not forming a solid this side, we cannot have a liquid electrode. What do? Let us use an inert electrode. In this case, we use platinum as our inert electrode. In a situation like that, where you have an inert electrode, the half reaction should have platinum at the end. So here, you see we are moving from ion Fe, so we put Fe here, to form Fe2 plus, so we put Fe2 plus aqueous here. But then we have these ions here. A paramanganate ion here, so we put this ion here. We ignore, you ignore the electrons in both cases. Then we have hydrogen ion, so you add also the hydrogen ion. And then you have manganese ion, so you add the manganese ion. So because they are in one solution, you don't make barriers for these. They are in one solution, therefore no barriers. You just put them together. Then you add a barrier. Once you add a barrier, then you can put the platinum electrode at the end. So that at the beginning we have a solid, at the end we have a solid. Only that this platinum is not being formed there. The platinum is just there to provide surface for this. So in this reaction, this part is oxidation. After the salt breach, this part is reduction, while this one is just an inert electrode. So that is a line equation when you have platinum or when you have an inert electrode. So as usual, the electrons will move from anode all the way to cathode. So now if you look at this cell, we have two electrodes here. We have the anode, which has zinc, and we have the cathode, which has copper. Each of these have their own electron potential. I mean, the potential maybe to repel electrons, the potential to gain electrons. So they have their own potential. So we'll say the zinc has potential 1, potential zinc, and the copper here also has potential copper. That is electrical potential or something like that. Now, the potential difference will be the voltage difference between the copper and the zinc. So really, PD will be given by the voltage of copper minus the voltage of zinc. So when you have a cell like that one, the potential difference is known as electromotive force. In other words, EMF. So instead of saying EMF, the potential difference of a cell, we just use the word like cell potential has a symbol E naught. So E naught stands for cell potential, but that is just the voltage difference or the electromotive force. That E is coming from here, the electromotive force. So it's the potential difference of a cell. Now, E is given by E naught, or for the whole reaction, is given by the E cation or E cathode, not cation. So the potential difference E is given by the potential of the cathode minus the potential of the anode. So that is the electromotive force of this cell. That's why we are saying it's given by voltage of copper, which is the cathode in this case, minus the voltage of zinc, which is the anode in this case. So in terms of the cell, the E, our cell electron or our electrochemical cell, we have a salt bridge. So really, the salt bridge will allow counter ions to flow from one solution to another, but it does not allow the ions that are actually involved in the reactions. So these counter ions are not involved in the redox reaction at all. But then if you don't have these counter ions, there will be no complete circuit. Right? So the charges will just build up on one electrode and then stop the whole reaction. That's why you need those counter ions in there. Then you have anode. So oxidation occurs at the anode and electrons flow away from the anode. We have cathode. Here reduction occurs, electrons move towards cathode. So if you look at the salt bridge, the counter anions will flow from the salt bridge into the anode solution. That's why we call it, the electrode in there is called an anode. While counter cations will flow from the salt bridge to the cathode. That's why the electrode over there is known as a cathode. Now, if you want to measure electrode potential, you cannot just use a single electrode. For example, let's say this is a zinc electrode. I cannot measure the potential of zinc just by using zinc alone. I need to use something else. So in this case, I'm using copper and connecting the two. So I will always measure, or I will measure the potential of zinc in relation to copper, or I'll measure the potential of copper in relation to zinc. But I cannot measure the potential of one electrode only. That is impossible. So to help with that, we came up with a standard electrode, so that we can use that standard electrode and connect it to other electrodes to measure the potential of those other electrodes. And if you are having a standard electrode, you need to give it a value. So in this case, we have a standard electrode that we call She, standard hydrogen electrode. This electrode, by convention, has a potential of 0.00 volts. So what we do, we can connect other electrodes to this She. Then we can read the other electrodes. So the value we get will be the potential for those electrodes, because we have said the value of She is 0. So this is the She, the Majesty. Now, how do you use that? For example, you want to measure the cell potential for zinc, but we say you cannot measure the potential of zinc without another electrode. So what you do is you connect zinc to that electrode, and then you have a reading. Based on that reading, then you can say, you know what, the zinc has a reading of 0.76 volts. But actually, you did not just measure the reading of zinc. You measured the reading of zinc in relation to She. Standard hydrogen electrode. You can do the same thing So what we are saying is when you connect the zinc to when you connect the zinc to the She, so this is reaction for She, the standard hydrogen potential. If you connect the zinc to She, zinc is going to lose electrons. So the zinc will be the anode and the She will be the cathode. But for that cell, we know that E cell is equal to the E cathode minus E anode. So here our cathode is 0.00 V minus our anode is minus 0.76 V. When you subtract the two, you got positive 0.76 volts. So one thing, in a spontaneous redox reaction, E is positive. So E naught is positive. So for every spontaneous redox reaction, E naught is positive. If E naught is negative, then it's a different thing altogether. So let's look at the non-spontaneous redox reaction. In this case, it's the same thing. The She is taken as cathode here, but here we have copper instead of zinc. So zinc is our anode. So we have our cell, this part anode, this part cathode. The cathode has a voltage of 0.00 V. The anode has a voltage of plus 0.34 V. Now our E cell is equal to E cathode minus E anode, which is 0.00 V minus plus 0.34 V, which gives us a negative. So this negative E means this reaction is non-spontaneous. If this reaction is non-spontaneous, it means the reverse reaction will be spontaneous. So I'll continue on the next video.